again. So Carsten will continue with molecular dynamics integration. Please, Carsten. So hello. You have to sit down.
Okay. So just to recapitulate what I was doing last time, the laser pointer. Right, what I did was I introduced 3 different simulation techniques: molecular dynamics, Brownian dynamics, which has temperature, and DBD dynamics, which resembles Brownian dynamics very much, but also does hydrodynamics and is a much more cost-based technique, and hence allows us to simulate much bigger systems. So, and I know, I think that Kelly was talking about Monte Carlo simulations also. So I don't want to say anything about what is Monte Carlo simulations, but I just want to offset the difference between molecular dynamics and Monte Carlo simulations. So basically, the goal of any technique is that we want to sample configuration of the average observables. And this could be pressure or temperature, kinetic energy, but it could also be structure factors, or it could be pneumatic order parameters, or you name it. And we want to average those over a lot of different configurations. And from statistical mechanics, we know that a certain configuration appears with a probability given by the particle function to the minus first exponential of the energy of that state divided by kBg. And basically, Monte Carlo simulations and molecular dynamics simulations are 2 different ways of generating such averages. In the molecular dynamics approach, what you're doing is you have the energy landscape, and you have the dynamic that is going to walk around the energy landscape, and in this way generate a number of configurations, omega, so that you can make this average. Monte Carlo simulations works in a different way by doing, should we say, artificial dynamic in energy space, but it still reproduces this Boltzmann distribution, and hence is a different way of obtaining these averages. So we can make a kind of phase diagram out of techniques depending on the importance of randomness and friction, inertia, and the gradient, which is by the gradient of the potential unit of force. And if we have if the dynamic is dominated by inertia, we have free flight, means that things just move completely irregardless of the energy potential that they're located in. This is not very interesting. But if we are somewhere between taking inertia into effect and the gradient, then we're doing Monte Carlo molecular dynamics simulations, but with a Newtonian dynamic. The Newtonian dynamic would be somewhere on this line. But we can also, as I've seen, couple in the effect of randomness and friction. And depending on how much we do this, we get inside the middle of this kind of phase diagram, where we would find Brownian dynamics, also ring dynamics, and also dissipative particle dynamics. And Monte Carlo simulations takes complete based on this concept of randomness, live down in this corner, and if we look at the possibilities of going from taking randomness and friction and taking the gradient into account, then we can also do hybrid Monte Carlo and followed by Monte Carlo techniques. These are also on this line. So essentially, what I have done is I've started out here and then walked inside the middle of this phase diagram. But right, what do we want to do? Right, the goal is to produce the maximum amount of science doing minimum amount of work. This is always good. I mean, the more results we get and the less we have to work, then the better it is. So what does this mean? It means that we need to obtain as many statistically independent confirmations as possible using the least amount of CPU time available. Because then we can estimate these averages of observables with good statistic accuracy using the least amount of CPU time required. And there is no clear answer. It depends exactly on the system you study and the properties of that system. So for instance, molecular dynamics, if we want to make studies of dynamic or transport phenomena and non-equilibrium phenomena, we need to use molecular dynamics techniques because Monte Carlo doesn't have a concept of time, so we can include time-dependent properties. Molecular dynamics is subsequently we want to simulate dense liquids. This is because if you do Monte Carlo simulations, you need to create a neighbor state, and it will be difficult to create neighbor states in dense liquids because they always overlap if you move any part slightly. We can use them for studying soft interactions. The harder the interactions they get, the smaller our delta T have to be in the integration routine, and for this reason the less effective they become. So the softer the better. And this is exactly why this particle dynamics wins. It has very soft interactions and allows us to simulate with a very large delta T. And finally, there's a technical requirement. When we do molecular dynamics simulations, we can utilize clusters. It's difficult with Monte Carlo simulations to use clusters. And this is technical, and I don't want to explain why. On the other hand, Monte Carlo simulations, ideally, if you want to have rigid constraints, are hard non-differentiable interactions. This is difficult, and hard non-differentiable interactions are very difficult to treat within regular dynamics context. One can treat rigid constraints. If we can make a model that is living on a lattice, this will be always faster to simulate with Monte Carlo simulations. But molecular dynamics is inherently off lattice because we have the vector of any position or any particle. If we have systems that are very difficult to calibrate, Monte Carlo simulations will also allow us to trick the system to finding equilibrium faster. And perhaps I'm going to talk about that in the case of polymers tomorrow. And it can also be easier to generate generalized ensembles using Monte Carlo as a technique compared to molecular dynamics. So, I mean, sometimes you get more science using one algorithm, sometimes you get more science doing another algorithm. Sometimes you need to combine them to produce anything. So, I mean, no universal, no simple answers there. It's just something you have to be aware of. Okay, further reading. This will be at the very end of my talk this morning, but you got it now. So Alan and Tilbury is an old book, but it has a very neat overview of computer simulations about liquids. This one, Frankel and Smith, I can also recommend. That is a very good book. It both covers molecular dynamics, Monte Carlo, discrete particle dynamics, and many tricks of the trades. This one has a big overview of more atomistic simulations, and also this one. So this, I would say, is if you have those 4 books on your bookshelf, you more or less know everything there is to know about molecular dynamics and Monte Carlo simulations. Okay, so that was what was left from the talk this morning. So now I want to focus on, if you want to make a simulation, what do we do, what do we need to do from a practical perspective? And if there's time, I'll end up doing a little geometry on my computer and analyzing it a bit for you. So the practical problem, we have some real system, we want to study using computer simulations. What do we do? Well, this is the problem that you are facing before you start doing any science with computer simulations. And there's a number of steps you have to go through. You have to make a model. I'm assuming that you have some physical system that you want to simulate, but you need to make a model of that system that describe its structures and their interactions and the relevant length and time scales that they will be interested in. So if you're interested in quantum phenomena, but you need to pick a model that contains all the electrons and the electronic degrees of freedom. If you're interested in material properties, you need to formulate a model that is much more coarse, so it has, but the relevant lengths and time scales are much bigger, so that we can study systems that are large enough to material properties. So again, the model you make depends on the kind of science you want to do and the kind of results you're interested in. You need to pick a dynamics that we can use to study the system, but the dynamics in the context of these techniques or molecular dynamics is what push us from one configuration of the system to another configuration of the system. And this will again depend on the kind of experiment perhaps you want to compare to. I mean, sometimes you want to do NPT ensembles, sometimes it's more relevant to do NPT, where you're fixed, you have control over the pressure, not just the volume. So there's different dynamics to pick, and some of them will be sensible when you want to study a particular system, some of them will be stupid when you want to pick the system once. We need to do the actual simulation, which means numerically running the model with the dynamics we picked on the computer, store the trajectory, and then what have we achieved? What we have achieved is that we know the time evolution of the system, we know the coordinates of all the beats that we use in our model, but then we have to analyze this. We have to ask, what are the good observables? I mean, what is the numbers? We cannot use 1 million coordinates for anything. We have to condense this 1 million of coordinates into observables that we can compare to experiments and tells us about the physical properties of the system. And this again depends on precisely what kind of simulation, what kind of science are you interested in doing. For instance, if you want to compare to a scattering experiment, it would be obvious to calculate structure factors and form factors. If you want to compare to polarization microscopy, right, you would need to calculate the nematic order parameters, and again, depends on precisely on where you want to go with this. And what we can then do is we can relate, we can make a sample any observables we are interested in, and we can study how these different observables are related. And for instance, what we would be interested in, and this is what I will talk about tomorrow, this is in the case of rubber. We want to study the microscopic polymer conformations when we deform a piece of rubber. We want to study the mesoscopic structure and how it depends on the deformation. And we want to study what are the macroscopic material properties. And we want to relate microscopic conformations, mesoscopic structure to macroscopic material properties, if we want to study rubber. So I will give you a 1-hour discussion on going from there to there to there tomorrow. That will be the goal of tomorrow's presentation. So let me look at each of these steps a bit more in detail, but still a bit superficial, because I do not want to teach you to simulate something particular. I want to give you a kind of idea about what we need to think about for whatever system you could be interested in simulating. And a very important property is that of universality. And this is a property of physics that means many different models actually describe the same physical system. Here we have, and then the point is that not all models are equally easy to simulate, so you want to pick the model that is most easy to simulate. So what is this? So for instance, if you have a polymer, like this would be polyethylene, you can do an atomistic model where there are all the hydrogens and carbons. That is certainly one way to represent a polymer molecule, but it's expensive to simulate because there's many details. You can also just describe it as a three-dimensional curve in space. That would be a continuous model. This is again complicated to simulate, but this is what theoreticians like. And then you can do half-useful formalism on Hamiltonians of continuous curves in space. That's very beautiful, we just cannot simulate it. Or we could take the polymer and describe it as something that is living on a lattice. This is very efficient if you want to do Monte Carlo simulations, but it will not teach you anything about the dynamics of polymers. Or we could pick each spring model, so instead of simulating each hydrogen, each carbon, we can lump together many monomers into one single bead, describe the polymer chain as a chain of beads that is connected by springs. And this happens to be a very efficient model if you want to do molecular dynamics. So the point is, the same system can be described by many models. You will get out the same physics in all of these models, but this one is by far the most easy to simulate with molecular dynamics, anticipated particle dynamics, and this one is by far the most easy to simulate with Monte Carlo simulations. So again, it depends what are the physical properties that we want to study, what are the models that we pick. And this is, I would say, this is a kind of engineering in some sense, because we have to have a bit of knowledge and make the right choices. not science. Another important thing is coarse graining. So the idea is that we assume that you have a detailed model of a system. The question is, can we make a much coarser model based on beads rather than atoms that contains the same physics as the detailed model? Due to the fact that the coarse-grained model has fewer degrees of freedom and simpler extraction, we can simulate it much faster. Alternatively, given the same CPU time, we can simulate much larger systems with coarse-grained models and fine-grained models. But of course, being coarse-grained models means that we are not going to learn atomistic details anymore. We throw away the possibility of learning something atomistically or on the Leibniz level of learning something about the electronic transitions. This we throw away. On the other hand, we get a model that allows us to simulate a very big system, so we can talk about elastic properties, for instance. We cannot talk about elastic properties of a single molecule. We need thousands and thousands of molecules interacting with each other to create a small piece of material that we want to study. So some concrete examples of the concept of coarse graining. Here you see different molecules. You see their atomistic representations. And what we want to do is we want to take some of the atoms, group them together in beads, and then describe what is the interaction between this bead and that type of bead, or between two like beads. And then we can write down, instead of writing down what are the hydrogen-carbon and carbon-carbon interactions, we can write down what are the bead-bead interactions. But for instance, if you want a detailed model, we might have to treat the end of this chain with a slightly different interaction than the bead inside the model. You can also see where the double bond instead of single bonds we need to make sure that we have the possibility of representing this in terms of a different interaction. So each of the beads, by each of these colors, we have to specify an interaction. This is work from Magnus Christiansen's group, and they started out in mines. You can see, depending on different molecules, you can apply this concept of coarse graining to coarse beads, but they're going to be slightly different. And actually what these guys showed was that you can use exactly the same interaction potential between these two beads, those two beads, even though it's different molecules, you can use the same interaction potential between them and actually reproduce experimental results for these three different molecules. If you want to simulate the monomers, this is polyethylene. What we can do is we can take n monomers and lump them together in a bead. Right? A bead will then just have a single center of bars of many of these atoms. But now we have to specify what is the spring constant between these beads, what are the angular potentials between them, and what are the torsional potentials, so that the chain of beads reproduce the same statistical properties as the real polyethylene chain. This is another concept of coarse graining, or another version of it. We can also take more complicated molecules, so this would be polycarbonates. And here you can see that what they've done is that they take parts of the molecules represented by different style beads, and then we specify again what are the interactions between different types of beads. So, and the famous group in mines have done a lot of work on exactly coarse graining of this molecule. And of course we can make more and more refined coarse grainings and approach being able to predict the properties of the molecules more and more accurately. So again, it's a trade-off. How much detail do we want, how much accuracy do we want, and how smaller systems or how big systems do we simulate. Another type of coarse graining is actually what you do when you jump from a Newtonian dynamics to Langevin dynamics. And here we have an atomistic simulation of 100 atoms and 1,000 water molecules. But what we can do is we can replace this molecule by a very simple model where we just have 10 particles or 10 beads, but we can represent the effect of the solvent through the friction and the stochastic forces of the Langevin dynamic, or the dissipation particle dynamics. So in this sense, what we've done is we've coarse-grained away an explicit solvent into an implicit solvent. And this is another way of coarse-graining. GFCx coarse graining allows us to make coarser models but simulate bigger systems. And this is the statistical mechanics of how to coarse grain. So it's only 2 slides, but it's a bit daunting. So I'm assuming that we have a system in the INCT ensemble, and we have a microscopic description. So for instance, all the coordinates here would be the coordinates of all the atoms. And I assume that we know the Hamiltonian of the full system, for instance through a quantum simulation or through atomistic force fields, such as Aula or other atomistic force fields. What we can do is we can define a fine-grained or detailed partition function just by integrating over all the coordinates the Boltzmann factor. And here beta is 1 divided by kbt. And we know that we can get out the free energy if we take minus kbt times the logarithm of the partition function. And this is basic statistical mechanics. The point is now that what we can do is we can invent a mapping that takes all the coordinates, all the microscopic degrees of freedom, averages some of these, and returns us, for instance, the center of mass of a group of atoms. I call those capital R. So these would be coarse-grained positions of the beads that we use to represent the model. So I can say that we have a coarse-grained description of the system in terms of where are all the beads. Of course, there's much fewer positions of beads than there are positions of atoms. Then we can define a restricted partition function, a coarse-grained partition function, which is a function with a number of particles, volume, and temperature, but also a function of these coarse-grained coordinates, which is given by essentially the integral of the fine-grained representation. But now we have to add a delta function, making sure that the coarse-grained bead positions are in agreement. So basically, we only sum the exponents when the microscopic configuration is in agreement with the coarse-grained representation that we specify. So this becomes the coarse-grained partition function. Again, a function of all the coarse-grained positions. And what we can do is that we can calculate now a free energy potential, or potential mean energy is called, which depends on all these coordinates, but is given by minus kbt times the logarithm of the coarse-grained partition function. And we know then that we can just calculate the true force, not the free energy, now it's a force, by taking minus the gradient of this potential. But what you can see by doing this exercise is that we can only do it in equilibrium where we know statistical mechanics apply, and furthermore, the force field now depends on the state point. It depends on the EFT. So you can change the temperature. In principle, we have to go through this entire equation once more to calculate what is the effective attaching potential at a different temperature. So, analytic coarse graining assumes that we already know a fine-grained atomistic representation of the potential. More often than not, this is not the case, but if we do it, then we can make a systematic coarse-grained model. And what one can actually do is one can make a hierarchy of coarse-grained models and actually work both ways. So you can also take coarse-grained representation of the system and introduce the atomistic coordinates again. In this way you can actually simulate, but you can take a polymer system, make a coarse-grained representation, equilibrate the coarse-grained representation, put in the atomistic representation, and make short simulation of atomistic detailed things. This is called multi-scale modeling. This is pretty much fancy of any time. So, but most of the time, most of the time we do not know this fine-grained potential. So we need to make an inspired guess of what are the exact potential, perform simulations, compare to experiments, and go back if we get the wrong result. So this is trial and error. In most cases, it's trial and error. Okay, so that was the part of discussing models. Before I can discuss how to simulate something, I need to introduce a few tricks that actually makes it possible to simulate those things. So one very important question is, when you do a simulation with a naive molecular dynamics routine I showed you, what happens is that you spend by far most of the time calculating the forces. So the question is, are there optimization tricks that we can apply to calculate forces faster? So idea can be invent methods of keeping track of which particle pairs are interacting such that we reduce the time spent calculating forces. And the very worst case is that in particles, they could in principle all of them be interacting with each other, in which case we need to calculate something which is n squared half pair interactions. And to calculate at each time step n squared interactions is prohibitively expensive. And if we didn't have clever algorithms to get around this, I mean, nobody would be doing molecular dynamics simulations of more than a handful of atoms or a handful of beads. And what we are running, what is state of the art is in millions of beads. Right? So there's a very big difference between having algorithms that takes O of n or O of n squared. While O of n squared is a million times slower to simulate. And when we are running things on the time scale of where it takes a few years to complete simulation, right? We cannot wait a million CPU years to get our result, but then funding will run out, and life will run out, the universe will run out. So, just to return to the basic molecular dynamics routine, right? We initialize the particle positions and velocities. This takes an amount of time which scales linearly with the number of particles. Then we have to repeat this loop, where we calculate the force, and in the worst case, the force scales as n squared, because the force is particle pair interactions. So we need to know the pairs, and this is approximately n squared. The Valetta algorithm, we use this to update the positions, and this again just scales linearly with the number of particles. We have to sample the configurations every once in a while, and this takes nothing, and we have to update the time, and this takes nothing. But this is where in a naive molecular dynamics routine we spend all the time. So can we do better? And the first step to do better is to assume that the interactions we have are short range, and they are characterized by a cutoff distance called RC. So this ith bead is going to be interacting with everything inside the distance RC from the center. It's not going to interact with anything outside because we assume that by this time the interaction potential has decayed to zero. So now the point is that we can create a list where the ith particle has a list of where are all its neighbors. And this of course looks very clever, but we don't gain much from it. And this is because if we look at the number of neighbors of a particular bead, then this is the, so n divided by v is the density, and what is m? What could m be? I've forgotten what before this. Okay, I think if you want to calculate n different pair interactions, it's the question is how many neighbors does every particle have? And this would be like the number of pairs or the number of atoms you want to update. How many neighbors do they have? And this scales as n squared. So it means that we have to again evaluate n squared distances just to figure out who are close to each other. There is a slight advantage which is that we can reuse the list. So for instance, every 5 or 10 iterations, we have to calculate the list because only particles are moving, but we can at least use the list maybe 5 times. So we don't have to calculate it every time step, but only, let's say, every 5 times step. But we haven't really achieved much because it's still an n squared process. And if you look at the construction, if a bead inside or just on this edge of the Valetta distance here, if this moves inside the sphere of interactions, then this interaction has to be included. But if this particle, it diffuses around and ends up inside the cutoff distance from particle I, this particle I and this bead would be interacting. So we need to update the particle, the Valetta list, faster than essentially the motion from outside to to inside. And this also gives us a rule for updating. We have to update either with a certain frequency or at least so often that no particle have moved inside the interaction cutoff. Otherwise, the algorithm would be interacting pair interactions, and we would be producing the wrong physics. So there's a way of optimizing this, and this is to apply a linked cell list. And what we do is you take the entire simulation box and sort beads into the box, into the subcell of the simulation box where they live. And this can be done O of n, so this takes linear with the number of particles. And now we know that if you, for instance, have the particle A here, and we want to calculate what are all the neighboring beads inside the valley cutoff distance, we can start out looking only in the neighboring boxes, because we know if something is in the box far away, it will be outside the valley cutoff. And by applying both a linked cell list and a valley list, we can calculate, or we can get down to O of n, which means that the force evaluation will be linear in the number of particles. So what would the algorithm then look like? Well, we have to initialize the particle position as before. We have to rebuild the neighbor list to figure out where, in what cell are all the beads, and what are the valley lists of all particles. Now we can calculate the force acting on the bead, but using the neighbor list we have. And what we've done is, by this exercise, we converted this from an n square process into an n log process. And again, this is an in process, and these ones doesn't care. But then every once in a while, we have to work on rebuilding the neighbor lists. But again, this is an in process. So the entire result of this is that when we run around in this loop, it scales linearly the number of particles rather than n squared. And this is a factor of 1,000,000, but this could be a factor of 1,000,000 in terms of optimization of algorithm. So this makes a lot of difference. I mean, I know this is this is technical details, and I'm discussing this because when towards the end I will actually show you how to do a simulation, and you can send me an email. I'm going to send you the input file so you can run it yourself, right? And you should know what you need to specify to run a simulation and what you need to be careful of when running simulations. And one thing you have to be careful of is if these lists are rebuilt often enough. Otherwise, you can be producing complete bullshit.
What does often enough mean?
It depends on everything. That depends on the length scale, it depends on density, I mean, it depends on the kind of system that you're simulating. So there's, but the point is you should have all the pair interactions. So you should rebuild these lists often enough. Right? But you should also rebuild them so rarely that it's not an appreciable amount of this few time you spend rebuilding this. And this is a number that you have to figure out by essentially trial and error.
So you are increasing the number of rebuilding, or the frequency of rebuilding the list, and then you see now this doesn't pay off anymore, so this is not necessary anymore.
Yeah. Yeah, I mean the code
of 1.2 or something.
Yeah, I mean the code will tell you if there are dangerous rebuilds where particles have moved too far. And if particles move too far, you need to rebuild often, more often. So that's it's something you have to check and be aware of. Okay, I do not want to talk about long-range forces, except just mention that they exist. So far I've assumed that all forces have a cutoff distance that is much smaller than the simulation box. But for instance, we know Coulombic interactions are 1 over r, the long range. And how can we treat long-range interactions? And what happens is that we need to basically calculate the interaction between a particle, not only its neighborhood, but also the periodic images of the entire simulation box, including the particle itself. So particles will be interacting with themselves and everything. And there are complex techniques based on image information and an optimization called particle mesh techniques, which makes use of Fourier transform techniques. And when you do this, you can get it down to scale as n times log n. And if you do not use the fast Fourier transform technique and the particle mesh optimization, the Ewald summation will be into the 3 halves. There is another way, which is if you say that you don't just use the forces, but you can do a multipole expansion of the electrostatic interactions, then it becomes O of n, but the prefactor is so large that this is often very expensive to calculate. So the point is, well, I just for completeness want to mention that long-range forces can also be treated, but in order to, I mean, if I had to explain how to do this, this would be at least 1 hour of terrible details about conditional convergence of series, and it's very technical and not very interesting. Then the second point is, if we have lots of computers, can we use them? I mean, typically, right, what we want to do is, of course it's nice to have 1 computer, but if you have 1,000 computers, can we run things 1,000 times faster? So let's say, okay, now I'm taking 1024 because it's a nice whole number. Let's assume we have this many computers. Can we make them produce science for us? And this goes to the problem, how much of a simulation can be distributed on so many computers? So here this is a picture from one of my rubber simulations. There's 1 million beads in the box. But if you run a system that large on a single computer, we will get nowhere. So what we need to do is we need to run it on many computers, where each computer just owns a separate section of the entire system. This creates additional complexities. So here I'm assuming we just have 4 nodes, and node 2 owns everything inside the red box. But of course a particle here is also going to be interacting with particles inside its neighborhood. And the neighborhood, which are the ghost cells, are controlled by node 1. So how can we treat this? And the way to treat it is to make sure that node 1 tells node 2 about the coordinates of things in this ghost layer. And when node 2 has calculated the force between its particle and its ghost particles, it has to inform node 1 of what is the force it has calculated, because this force, of course, also applies between the particle owned by node 1 that is interacting with the particle in node 2. And this becomes very complicated in 3 dimensions. So this is just to point out the fact that you have ghost particles and you need to have communication when you use more than 1 computer. So a real parallelized molecular dynamics algorithm would be something like this. Again, we need to initialize the configuration. We need to build neighbor lists. We need to distribute particles to all the CPUs that we have available. And now we have to repeat on each node that we receive the ghost positions of particles that are owned by neighboring CPUs, but that are interacting with particles on the current node. Then we need to use the neighbor lists, but they also need to be aware of this complexity of having multiple CPUs. But again, we can calculate the force using ON computation. We need to inform the other CPUs that we have calculated ghost forces and tell them to add these ghost forces to their particles. And again, we just use the very algorithm on each node. Then we have to wait until all the nodes are done, because they have to be synchronized with each other. And this means that if systems have very different densities, that will be bad, because all of the CPUs will be waiting for the ones with highest density. And then again, once in a while, we need to rebuild neighbor lists, and we need to communicate particles. If a particle has moved from one node to another, we need to communicate through the network that it has moved, and who is now responsible for owning this. And we have to update time, and again, sample configurations and so on. So this is a schematic algorithm of what a real parallel molecular dynamics algorithm would be. And this applies both to the molecular dynamics, Brownian dynamics, and dissipated particle dynamics. Because it's essentially, you add a bit more forces, but the logic of everything is the same. So we can calculate efficiency. So let's say that we have NP processors available. We are working on a task, and that task we can characterize by the amount of work that can be done in parallel and the amount of done that can be done in serial. So if we have, this is the work that where we get 100% use of all the nodes, and this is where we can basically just run on one node. And these two have to sum to 1, and you can calculate the speed up given by this equation. So if you have a job that is 100% serial, it means the WP will be 0. And if you look, what you can see is that the speed up of running such a job on P processors is going to be, so this one is 1, that one is 0, is going to be 1 divided by the fraction that can be run in serial. If you can run the entire job in parallel, this one is 0, and we get a speed up which is proportional to the number of processors available. So if it's 100% parallelizable, right, if we have NP processors, we're going to run NP times faster. If it's 100% serialized, irregardless of the number of the processors which throughout the job, is going to take the same amount of time. And this is what is plotted here. The ideal speed up is linear number of processors, but depending on how much time or how much of the task can actually be run in parallel, right, we can get much, much worse behavior. Right? And again, this depends. Sometimes it means that if you throw many CPUs at a job, it's going to get slow and slow and slow. So again, there's optimums that you have to figure out by trial and error. So here is a real example. Now the efficiency is scaled to 100. So 100 is perfect linear scaling with the number of particles, and it's a system of 32,000 Jones particles at standard conditions. And what you can see is that when we run more and throw more and more processors at this, the efficiency goes down. And of course, this is because each of the node gets fewer and fewer and fewer beats it has to simulate, but it gets a larger and larger and larger surface with the neighboring CPUs that has to communicate more and more. And for this reason, the scaling goes down like mad. So this would say, well, let me say that a bit later. But this is also a bit cheating, because the more CPUs we throw at the job, the less work each CPU has. So we can do another thing, we can keep the number of particles per CPU fixed and see how the scaling goes instead. And what you can see is, if you keep 32,000 particles per CPU, the more CPUs we throw at the job, the larger the system we can simulate. And we are simulating at about 90% of the maximum efficiency. Right, so this is good, and this is what we want to achieve. Right, so the lesson is, if you want to apply many CPUs, use big simulations, because a small simulation is not going to give you much in terms of speed up. So if you have more CPUs available, potentially you get the results faster, but not always, because it always requires more communication overhead. And this also means that when you buy computers, one thing is how fast is the computer, but another very important thing is how fast is the network, because this is what determines how fast the computers can communicate with each other. And we always get suboptimal CPU scaling, but for good job, maybe this is 90% of the perfect ideal case. And in that case, we can live with it. So in practice, what does this mean? Well, let's say we have a job. It takes 2 CPU years to run. So this means that it takes 2 years on a single computer. From you start it to we get the result. In practice, we cannot wait 2 years for getting a result. So what we can do instead is we can throw 12 CPUs at the job. Then, ideally, it will be done after 2 months, but because of this sublinear scaling, it means that it will only be 90% or 80% done after two months of simulation time. If you throw more CPUs at it, it will be done after 1 month, but only 17%, right? So the more CPUs we throw at the job, the longer it takes. We get the results faster, but we also, are doing less effective computation. So again, there's an optimum. Okay, so these were the kind of technical details. So now I want to do something practical. which is basically to give you a small introduction to simulating a Lennard-Jones liquid, and then I will give you a small introduction to lamps, and I'll run the Lennard-Jones liquid on lamps, do a bit of analysis, and show you, what are the steps that you need to do when you actually just run the simulation. Because then I hope that when you say this, you're going to say, wow, this is fancy, and you're going to download lamps, and you're going to email me for my input file, and then you're going to run away with this, do a lot of science, and improve the field. And I think when you talk about simulations, right, I cannot do a practical experiment, but at least I can do a practical simulation. And again, the simplest thing we can simulate is a Lennard-Jones liquid. So I'm going to take that as an example, because if there was a tutorial and you had to do it yourself, right, a Lennard-Jones liquid would be the first job you would get. So what do we want to do with a Lennard-Jones liquid? What we, for instance, could do is we could sample thermodynamic properties of such a liquid. These would be, for instance, temperature, pressure, kinetic, potential, and total energy. We want to calculate response functions, and one of them would be, for instance, the diffusion constant of the particles. And another one would be what kind of structure does this liquid have, and we can characterize that by pair distribution functions. And I'm going to introduce those in more detail now. So by far, I think the most complicated thing when you do simulations is actually to figure out that the pressure is given by this expression. And I'm not going to prove it or go into terrible detail, but basically, what we can do is we can define a tensor, which is called the virial tensor. It's called the virial tensor because these kind of things where you have distance tensor product with force, these are called virials. And what you can show is that this tensor, well, it has two contributions. It has one from the velocity of particle I, where alpha could be the xyz component, times the velocity of I, times the beta component. Like this is 2 times the kinetic energy of the ith particle, and the alpha beta Cartesian component of this thing. So, and of course we are assuming that the different velocity components are uncorrelated, so this just becomes 2 times the average kinetic energy. And we have to divide by volume to get the right dimensions. And then we add this term, which is called the virial term. And it's a long calculation to show that this is in reality a good thing. But what we can do is we can define the pressure as the xx, y, and z components of this tensor divided by 3. And this, which is called the stress tensor, is actually also a way to measure the stress if you want to deform a system. You can study how this tensor changes with the deformation of the system. And I'm going to return a bit to that tomorrow. I do not want to prove this equation, or if it's ugly, but what I can do is I can at least derive it or reduce it in a special case because they are the ideal gas. In the ideal gas, you don't have any interactions. If it's equal to 0, we can say, well, there is no difference between xx, y, and zz, and I can assume all particles have the same mass. So the pressure, right, is the average of these 3 components, but these 3 components are the same by symmetry. So I can say the pressure is just the xx component, which is this expression. But because the force is 0 in the ideal gas, this virial term drops out, I get only this, which is essentially the kinetic energy. And I can simplify it, and if we are summing over n identical particles, we just get an n prefactor outside. And what is the average of velocity squared? Well, this is one of the contributions to the average kinetic energy, but we know through the partition theorem that each quadratic degrees of freedom carry 1/2 kbt. So this is nothing more than kbt. So what I've done is I've started out saying pressure is equal to density times kbt. If I multiply V to the other side, right, I get the ideal gas equation of state. So this is a complicated expression, but in the case of an ideal gas, it does immediately reproduce the ideal gas, which otherwise it would be stupid. Okay, I don't think I have much time, but yeah. One thing we can do is, since we have the coordinates of all particles, we can look at how far have a particle moved in a certain time delta t, we can look at this quantity squared, and we can average it all particles. And this is called the mean square displacement. And it's easy to show that the mean square displacement is given by the diffusion constant times the time that we're waiting. So this allows us to measure diffusion constants in the simulation. In the pair distance distribution function, if I have a liquid, I can pick a bead and I can count inside a certain spherical shell how many neighboring beads are there inside this shell. This is N of R. But I can also calculate what is the volume of this shell. This is V of R. And if I take this ratio, what I get is the pair distribution function. And then what you can do is easily you can Fourier transform the pair distance distribution function, and what you get is the pair distribution function in Fourier space. And this can actually be directly measured in scattering experiments. So this is a nice thing to measure. And just to show you what it would look like if I have a gas, the particles cannot overlap. So at short distances you have zero pair correlation. Then you have a peak because there could be some kind of shell structure, and then it's essentially 1 because it's the background bulk density. As if they become more dense, you get more structure because each particle has a more clearly well-defined shell and second neighbor shell, third neighbor shell, which is what these peaks represent. And if you cool it or compress it by the crystallizers, you get a lot of peaks, and this is known from scattering theory, or how you infer the crystal structure from peaks. So the kind of system that we're interested in is a Lennard-Jones liquid, and just to show you, this is the kind of pair correlation function you get, which is very reminiscent of the hard sphere pair correlation function. You can see they are almost identical. And if you Fourier transform, it looks exactly the same way. And again, this is something that you can obtain through measurements. So just a small advertisement for lamps. I mean, I don't have any, I mean, the people that make lamps doesn't give me any money for this, but it's open source, you can download it, it's relatively easy to use. There's a huge user community that is adding new functions to it. It's also easy to add functions to it. So it's a pretty good tool if you want to start out doing simulations. I think what you should not do if you want to do simulations is to start writing your own code, because it's going to take half a year writing the code, and then it's going to take 1 year to find all the bugs. And if you even parallelize it, it will be a PhD until you get the right code, and then you don't have time to produce results. So, I mean, I would suggest download the damn thing. Produce science, do not produce code.
If you find an error, you can publish it.
You just email it to Steve Crimson and he'll fix it. There's new version of LAMPS coming out every other day. So I mean the simulations I'm showing you will be from the 2nd February version of LAMPS. Okay, so what is LAMPS? It's a classical molecular dynamics code. It stands for large-scale atomistic molecular massively parallel simulator. So what it does is it does all these tricks I showed you. This is already implemented in LAMPS. It has well-defined potential for soft metals or soft materials, biomolecules, polymers, also solid-state, things like metal, semiconductors. What I'm interested in the coarse-grained and mesoscopic systems. You can model atoms, but I think where it excels is at the mesoscale. And you can actually also couple mesoscale to continuum finite element modeling. It runs on a single processor or it runs on a cluster, and it's optimized in many different ways. And it has a nice feature that you can modify and extend it. So you can just, when you have the code, you can write your own code. It's not terribly complicated, but it may take a few weeks to understand how to write something new. But this is nothing compared to writing your own ED code from scratch. This is year amount of work.
But you use C++?
C++. So just some of the properties of what I think would be a good code. It has to be easy to modify and extend, also to debug. It has to be fast parallelized. Right, we need to get much science out of as few resources as possible. A practical thing is, I mean, software should always write output in text file and never in binary formats. I hate binary formats because 10 years from now, nobody can write or read results in a binary format. But 100 years from now, you can read it if it's a text file. And when you have many computers and many architectures and they don't always use this Indianness convention, binary is just a major game. So text files are easy and they're not much larger. Open source, I think from a philosophical standpoint, right? If I contribute to a code, I want all of you to use my contribution too. So it has to be open source and not owned by some stupid company. And if there's a large user community, it means there's a lot of people that are doing your work for you, right? There's a lot of people out there that has exactly the same problems as you, and that might already have implemented all the code to solve your problems. Right? So having a large user community is always a good thing. Okay, so what do we need to do when we run a simulation? We need to generate an initial configuration. We need to write a script that specifies what are all the interactions, how should it be integrated in time, and so on. We need to run it, we need to analyze the results, and then we need to write the paper compared to theory, of course, all of that. So let me just do it. How much time do I have?
5 minutes.
5 minutes. Okay.
I can get it tomorrow. Right.
So this is just a short introduction. I mean, with 5 minutes, I don't want to go into detail, but this is just what LAMPS looks like. So you need to specify how to run the simulation. This is also a single text file. For instance, I specify atom style atomic. This is because atomic means that you have beads with positions. If you want polymers with angular interactions and charges and so on, there are other styles for doing more complicated things. Always use the simplest style because then you don't waste CPU time. Read data, we need to read in the initial configuration, which is called config.input. And what does config.input look like? Well, it specifies how many atoms are there, how many types of atoms are there, how big is the simulation domain, and what are the coordinates for the atoms. So these are just random, I just put them in randomly. Then we need to specify what are the velocities. I just generate a Gaussian distribution of velocities with some average 1.5 or 1.10, doesn't really matter. Now there's a crucial point, because the initial configuration I've made is of random positions, right? I put them in randomly. If I start random positions using Lennard-Jones interactions, right, a certain number of the particles is going to be overlapping. And remember, the Lennard-Jones interaction looks like this, which means that I will have particles up here having infinite energy in principle. And what is going to happen when you simulate infinite energies is that you're going to get infinite forces, infinite velocities, and everything is just going to fly apart and it's meaningless. So how can we solve this problem? And the way to solve it is not to use a Lennard-Jones potential, but to start with a different potential. So what I'm doing is I'm starting with a soft potential that looks like, initially, it's just a cosine, a single cosine potential that cuts off in the zero at a certain distance, and then I increase the height of this cosine potential to push off particles until no particles are overlapping with each other. And this is what I'm specifying here. I'm specifying a soft cosine potential with a certain distance, and I'm specifying I want to start with a height 1 and end up with a height of 50 in terms of the cosine potential. Then a few details of the integrator. The integrator I'm using is an NVE integrator. What this means in LAMPS notation is just that it's a particular algorithm to update positions and velocities based on forces, but the forces are calculated using a Langevin dynamic, which means that, right, I have the friction and I have the thermal kicks in there, and I start up with a temperature 0 and end up with a temperature of 1, so I'm slowly heating the system with the Langevin dynamics. I need to specify a bit about how this cosine push-up works, and I need to specify I want to run the simulation in 2 dimensions. Then I specify what kind of thermodynamic information do I want to print. I want this depth, temperature, pressure, kinetic energy, total energy. So this is the first step, and I'm running that for 1,000 time steps. So that's far enough to take all the beads that are on top of each other, push them apart so they're no longer on top of each other. Then I remove everything that has to do with this push-off. I change the interactions into Lennard-Jones interactions with a cutoff distance of 5, and they have a epsilon and a sigma parameter of 1 and 1. Everything is interacting with Lennard-Jones interactions. I run that for 4,000 configurations, and this is because the initial state is that of a cosine potential. So I want to run it a bit further with this, the real potential to equilibrate things before I starting sampling configurations and analyzing configurations. Then I store the configurations every once in a while. I do some analysis that is going to turn up into a radial distribution function, and the mean squared displacement, so this is Lamb's technology or whatever, and I'm going to run that for 30,000 time steps. And now the boring thing is to run this thing, and if I just run it, right, this is what it looks like. It's very boring. You get lots and lots and lots of numbers. There's no graphical user interface whatsoever. And of course, this is because Lamb's is built to be run on a cluster of, how many nodes you want to use? 500 nodes. And then it's not good on your screen to have 500 windows saying click start. Right? So for this reason, it's very convenient to have a boring text interface like this. Right? I just ran the simulation, and actually what you can see here is the dangerous fields equal to 0, which means that my Verlet lists were rebuilt often enough as not to have dangerous configurations. And there's a lot of thermodynamic information that has been dumped. So what I've done is I've prepared a small script that processes all of this, which is called that. And what I can do is now I can just plot the thermodynamic information. So you can see I did the push off at short times. I'm going to have very strange things happening, but then I equilibrate, and for the remaining part of the simulation, the pressure is constant at 5. The kinetic energy, I think that should be, right, this is constant at 1. It should be constant at 1 because I specified in my simulation what the kinetic energy of 1. So in fact, temperature, the black curve is exactly identical to the green curve because temperature and kinetic energy is the same thing. And then the total energy drops down, and this of course is because you have a minus when all the particles are in the minimum of their neighbors, you get minus something. So this is, but this will give me the average pressure, the average temperature, and the average energy. And I can start to relate these to various things if I'm interested in that. Mean square displacements. What you see is that mean square displacements are approximately linear with time. So this slope, if I fit it a linear curve to that, immediately gives me the diffusion constant. Again, very easy to do. You also see there's some noise. I mean, of course, I should run the simulation for longer, but you would be bored if I did that. And you can also see there's some deviations for large time steps. And this is because the statistics is always worse for large time steps compared to short time steps. Because by what I'm doing is I'm calculating the average of distances or differences in time. So there's one contribution at the very largest time. Right? I know the initial configuration of all beats, I know the final configuration of all beats. But for instance, to time step 10,000, I have many contributions along the trajectory that is separated by 10,000. So statistics down here is better than up here, and this is well known. But of course, I could run the simulation for longer and produce better results. And the last one is the radial distribution function. You can see I reproduce a radial distribution function exactly like expected from theory. And I could fully transform that into everything with it. So this illustrates that it's pretty easy to run a simulation of a Lennard-Jones liquid. You don't need supercomputers to it. This text file, well, it took me 1 hour yesterday to kind of glue things together to produce this. So this is a starting point if anybody is interested in doing simulations. But here I can give you the initial configuration and the initial how to analyze these things if you want to start somewhere. Alright, so what we can start to study is how these results depend on the density. Of course, if you increase or reduce the density, pair distance distribution is going to change. The diffusion constant is also going to change. If you change the temperature, what is going to happen? We could ask, I had the cutoff of the Lennard-Jones potential at 5. Is that good or is that bad? I could also ask, what if we have different interaction potentials? Well, I've just picked the simplest one. We can do anything, right? And we could really do anything. We could start to glue these particles together, study more complex liquids and everything. The Lennard-Jones liquid is just the starting point. So, this is the starting point of discovering how the phase diagram depends on the position in the state space of ABT and the interaction potential.
What does the ABT mean? It's a student question.
Constant number of particles, constant volume, and constant temperature.
I was sleeping already.
You were probably sleeping. Otherwise, NPT would be the constant number of particles, constant pressure, and constant temperature. Right, so this is where you would do the most experiments. And you could also, in games, easily change so that you're doing the simulation under NPT conditions. But I didn't want to go into details. Okay, statistics, let me just, I have -5 minutes probably. So I just want to say one thing. If we can calculate averages, we can also calculate errors on the averages. But the problem is you should be aware that this often underestimates the error, because the configurations that you store in the molecular dynamics or in the Monte Carlo simulation are always correlated with each other, which means you do not have as many statistically independent data points as you thought you did. So the way to treat this is to block subsequent configurations to make block averages. Instead of having 500 configurations, maybe you block 10 configurations and produce 50 different estimates for the block average. And what you can do is you can make this ratio of the error of the observable and the error of the block. What happens is that this particular ratio is going to plateau off at a value, and then you can see if I have a blocking of 20 or above, that effectively is large enough to decorrelate the configurations that you have. And that is, then you know that also the true error on the average, but this is the error on the observable, but square root is divided by m and not divided by square root m. So the error is larger because subsequent configurations are correlated. Just something that you have to be aware of. Right, so to summarize what I've done, I've discussed course grading and how to make models. I've introduced some of the tricks that you need to know when you do simulations, because this is parameters that you specify when you run it. I discussed a few of the observables that we are interested in, if it's Lennard-Jones liquids. I just showed you how to run claims, analyze the results, and this warning about statistics. Right, so now you can do the Lennard-Jones liquid too. So that's what I wanted to say. And that's what it looks like. Questions?
I have time for some questions. Yes?
How do you introduce fluctuations on parameters, for example, temperature, concentration? Because we know that in actual systems you have the fluctuations of capacity, for example. In this simulation, how do you introduce this?
I mean, because of finite size, there's always going to be fluctuations. I mean, so it comes out of the dynamics. I mean, we don't specify it, put it in, but because we have small systems and because there's the randomness of taking out heat and putting in heat through the thermostat, right, that automatically gives us fluctuations. Also, if you have the system, right, and if you want to couple it not only to a thermostat but also a barostat, there's also going to be volume fluctuations introduced by the barostat.
But you said you have to fix, for example, the temperature as a constant.
Yeah.
It's a mean temperature.
Yeah.
If you go locally, the temperature could vary, for example.
It will vary, yeah. And you could also do things like having two temperatures in one simulation, so you can do two different thermostats and look at the heat flow between two. So you can play with many things.
Can I get parameter about subcorrelation, like Hurst parameter?
What is it? I don't know what is a Hurst parameter. But you have the configurations, you have the coordinates. Right, so you can calculate everything that depends on coordinates. If you want velocities, you can also, but I can also say velocities. So velocity correlation functions you can also calculate. Right? So, I mean, anything that you have an equation for, we can calculate. It might be expensive or difficult, but in principle there's no limitation. Which is also why I say we can make virtual experiments, because I could calculate, if we did a scattering experiment on the Lennard-Jones liquid, I already had the pair correlation function in real space, so it doesn't take any serious work to Fourier transform it and make a prediction of this is what you would measure in an experiment. If I glued together the particles to make small dimers, I could look at whether or not at high concentrations there will be orientational preference in a certain direction of these dimers. I could put in gravity and see how would the system respond to gravity. I could put in a charge that is spatially dependent. I could put in an electric field and I could simulate electrophoretic mobility and isoelectric focusing. I've done that.
Could you also simulate magnetophoretic mobility?
I think I can. I mean, because if there's a dipole coupling, I could give each particle a dipole, put it into a global field, and then see what happens. So yes, I mean the sky is the limit. You just need to write down the interaction potential and have a few computers.
What about the force field in the black hole? What kind do you have? Do you have, for example, you can mixture of the gas and or do you have your own force field?
I think if you want to use AMBER or these other well-known force fields, I think GROMACS. But I would use GROMACS instead to run such simulations because I think it's better integrated.
But
to tell you the truth, I'm not sure how well integrated AMBER and CHARM is in labs. I think you can do simulations, but I'm not sure it's should we say. I mean, then you might as well download a code that is more easy to run these kind of simulations.
What kind of force field do you have in the lab?
Many. I mean,
but you need to specify only the parameters and the equation of the equation that describes the interaction.
Yeah.
For example, for the strength is harmonic and also non-harmonic.
Yeah,
you need to select all the terms and put by hand the values.
Yes. You need to specify everything. And there's many different, I mean, bond potentials, angular potentials, dihedral potentials, pair interaction potentials, but there's many to choose from.
You select the equation and also put the parameters.
I mean, you specify the kind of interaction potential that lanes already know and the interaction parameters. And of course, if you have many types, you have to specify all the cross terms also. So, otherwise, and if it doesn't exist, you can implement it yourself. I mean, it's not terribly complicated to add more interaction potentials. And you also have support for particles with orientation. So you can have, I mean, like you could have anisotropic particles with Burns interactions or Everest interactions. That also works out in the box. So, but I think if you really want to do AMBER or CHARM kind of force fields, GROMACS is much easier to run than LENS. So, but for coarse-grained things, I can recommend LENS.
So nice, thanks, Carsten.